I'll introduce myself, even though you do know who I am. Dr. Conover, Adam Conover. Why am I doing this presentation on retro computing? Well, because I'm old. And like playing with toys from when I was a kid, I think is the main objective. No, there tends to be a lot more to it than that. What retro computing really is, well, it's kind of hard to describe because it really means different things to different people, but it's really about the history of computing. Going back to systems that were perhaps simpler, sort of a simpler time, so to speak. One of the things I want to focus on in this presentation is a little bit of the sort of the rationale for why people do this kind of thing. Why people are kind of into these old machines and have massive collections of computing technology. But also, there's something that's kind of relevant here. Years and years ago, many years ago, punch cards were the thing, and then, paper tape and magnetic tape and all this stuff. And there's a certain irony to the fact that we have documents, or at least, literally, stone, tablets that can go back thousands of years, and we have a written history, even if fragmented, of kind of world culture to some extent. But yet, things that might have existed just a few years ago can disappear. And this might be a little tricky right here to do, but just to kind of set the stage, one of the perfect examples for this is that back in 2008, and hopefully this is going to work properly. Back in 2008, there was basically an issue with NASA. NASA needed to go back and look at data that they had collected from the 1960s, 1970s moon launches. Well, it turned out that there weren't any machines available that could read the tapes. It was all done on magnetic tape, and they were gone, at least as far as NASA was concerned. Luckily, in Australia, they still had copies, but that didn't even do anybody any good because they didn't have a machine to read them. And I won't bore you with all that. That's why I put links in the slides. But IBM, with the help of IBM, they managed to find an old machine, an old tape drive that they could use and restore it and clean it up just to be able to read this data. So, I mean, we're talking about things, less than 50 years ago, or about 50 years ago, that are, that could be gone. And there's a certain irony to that, we think of digital data as being, we talk about backups, we talk about all these things, but yet within a few years' time, we can literally lose technology. And, that's kind of part of the whole retro computing thing. If you're interested, from the collector standpoint, I have 2 links over here that simply illustrate the historical computers and oldcomputers.net. Lots of pictures of old machines and stuff like that. You don't need to really go through every single one, but so there is this idea of preserving old technology because, well, hey, floppy disks, there used to be 8-inch floppy drives. No one has disk drives for that anymore. Good luck trying to find one. So, of course there's that. And one of the beauties of some of these older systems is that they are completely understandable to somebody who's willing to kind of dedicate their time to it. Unlike a modern cell phone is way, way, way more complicated than a lot of the machines were back in, say, the 1980s, kind of when I was a kid. And there's something to be said for a machine that you could literally understand inside and out. And I'll show that in a moment, the gory details of inside the machine. But you literally could have a fairly decent working knowledge of everything that was happening in that computer, from the hardware level right down to its firmware, the software that was running on it. because it was small enough. It was a manageable. It was a system that was manageable in in the brain of a single individual, and that, at least in my mind, is sort of the key to it. Excuse me, like why I continue to kind of like playing around with these old machines. And of course, hacking, augmenting old technology, bringing it into the current century, pushing things beyond their original boundaries, and there's an entire scene out there of people that are writing code for these old machines to do all kinds of crazy things that we're just like, you're like, how is that even possible? When that machine was built, no one ever thought you could do that. But completely unmodified, people just come up with little tricks. So it's almost like, puzzle solving in a way, with that, because you can understand that complete system. So even though my focus is going to be kind of on the 80s here, kind of my era, I say, why not talk from the experiences that I, lived well from when I was a kid. But it's nice to maybe take a quick look at the like really retro computing. I don't know if any of you guys have heard about the anti-Carith. I always mispronounce it. Anti-Carithera mechanism from ancient Greece, like literally going back to somewhere between 1 and 200 BC. Literally one of the very first working, well, wouldn't call it a general purpose computer, but probably the earliest recorded computational device in existence. And of course, this is what it looks like, when they dredged it up from the bottoms of the ocean or the Mediterranean Sea. But a lot of work went into restoring these things and so forth. I'm not going to bore you with entire videos, but just to kind of illustrate the kind of working mechanisms here. Like I say, I have a lot of these videos linked that you can kind of go back and look through. I just want to zip ahead to a little bit right here, just showing what it was for.
By turning a handle, one could position the two hands to indicate for each day of the year the exact position of the sun and moon, and a small sphere indicating the phase of the moon. In order to guarantee its exactitude, whatever the day or year chosen, a dial on the back of the mechanism shows the metonic cycle, which reflects lunar and solar cycles over a period of 19 years, corresponding to 235 lunar months. Above this, another spiral dial indicates eclipses of the sun and moon. The handle was used to advance the pointer to determine when the next eclipse would occur in the Saros cycle. As these operations were connected by the interlocking gears, the actual date of the eclipse showed on the other dial.
Oops, turn that off there. So, again, that's just something that kind of goes way back. This idea of machines that could do computing of some sort, to be able to, to predict eclipses, to be able to predict, well, basically astronomical phenomena. The concept of a computational device literally goes back well over 2,000 years. And that's something that, I believe is, at least personally, I think is kind of fascinating. Jumping ahead a few hundred years later, again, kind of working our way to the 1980s here, the Jacquard loom. This is something that is studied. If you took COC 109, maybe, sometimes you talk about kind of the history of computing. But this literally goes back to the 1700s, or even 16s to some extent, of using punch cards, like literally, cards on a loom, and it's hard to perhaps see here exactly, but this is like a spool of cards that had tiny little holes punched in each of the slots, or across the surface there, that would basically let a needle go through for this loom to weave really complicated patterns, which ultimately became the inspiration for IBM's quote punch card reader. This is kind of going into the 1960s, where data was entered into systems. I'm just trying to mute that. Data was entered into systems literally using, punch cards. That's how they were fed into some of the very first computers, where the holes lined up, just sensors, either mechanical or optical sensors, would just read them. And again, there's tons and tons of code out there that was written. Probably none of it's worth very much today, but good luck. And wrapped around a cylinder there for you can watch the the video, but just illustrate that these ideas, a lot of modern ideas came from an era when general purpose computers weren't even thought about. Skip over or briefly mention this, just kind of in that interest of kind of building up the history here a little bit, that Charles Babbage in the 1800s developed, Ada, I'll have to send you to the back for there, the back a second. So I just want to move this to the front. The Computing History Museum in Mountain View, California, I've actually been there. Was there once a number of years ago while visiting some family that I have out there. But this was a machine that was designed in the mid-1800s that was never built. You might ask, what are we looking at? Well, it's the modern build of it that cost a ridiculous amount of money to build up. Admittedly, off the top of my head, I don't remember the exact cost, but it was, in the hundred. It was millions. But this is a machine that was designed in the 1800s by a mathematician as a first general purpose computing device. These cogs that you see here are simply, well, what would be kind of considered the transistors in some sense, making connections and cycling through the data. And there you can see them turning the wheels, and they were programmed with punch cards. Punch cards drove how each of these cogs are going to move and turn, and data could be loaded in. There was actually some separate sort of mechanical levers and stuff for loading in data. For really general purpose computing, even a printing device was part of Babbage's original design. They could stamp using ink, actually spit out the output on a roll of paper, just like a modern cash register. Again, this is before electricity. Unfortunately, you never lived to see it built, but around the year 2000, well, it was 1990s, 2000-ish, started to put it together. And it kind of has this world exhibition kind of thing going on, where it does make its well, actually I think it's in Europe now, probably to stay. It's a pretty big thing to lug around and move. I can't remember how many tons it weighs, but it's pretty incredible. But again, this sort of retro computing idea, most of it is about hobbyists with gear from the 60s, 70s, 80s, 90s, and so forth. But part of the whole fascination is how these machines kind of came to be, and even just kind of working our way up to the present day here quickly. Oops, I just want to check out the. There we go. I just want to keep an eye on the chat myself just to see if anyone asks any questions there. But given our limited audience, feel free to interrupt, feel free to shout out whatever you want to know if you feel like asking something. IBM back in 1944, well, at least that they admit to, a lot of classified stuff, you know, obviously World War II was going on. Machines that were built, again, programmed with punch cards, for the primary purpose of performing calculations for like mortar trajectories and things like that. Things that would take, you know, hours or days to compute by hand, you know, could be done in just a few minutes. You know, the idea was that radio operators could say, hey, you know, we've got targets or whatever. We've got wind, you know, we need to know, you know, how much force to launch, you know, basically war. And a lot of the first electronic computers really came out of kind of World War II, and sort of the need to do calculations quickly, you know, for the purpose of launching artillery. But that aside, it drove a fairly significant number of advancements. And this is something that I didn't actually even know before I started putting this together, was that I knew of these machines, this and the next one, but I didn't know they were actually at Aberdeen Proving Grounds in this era. I mean, well before my time, but honestly, I didn't even know that. And I'm like, wait, Aberdeen? I didn't know it was they were actually stationed there. The ENIAC, which, and I apologize, I'll just, here, you can edit that out. Get rid of something here that shouldn't have been there. There we go. One of the very first completely digital, well, not completely digital, had vacuum relays and vacuum tubes, which I guess are digital, or analog technology being repurposed for digital. But using patch cords from the telephone industry, you know, basically they're the exact same types of patch cords that, you know, phone operators use, and which actually came from the exact same patch cords that telegraph operators used in the late 1800s, you know, early 1900s. But yeah, this was a machine that was designed at the University of Pennsylvania, and again was operating at Aberdeen, which that was the part I didn't know. I'm not sure, like some of that information might have been declassified within, you know, the years that since I've, you know, learned of the ENIAC many years ago, and you know, subsequently it's like, oh yeah, by the way, that was here. I'm not really sure when that was made public, but it's, you know, like 50 years and classified stuff a lot of times. But yeah, literally a machine that was programmed by running patch cords from place to place. Each one of these little units here, let me kind of go across here, were like part of a processor. It was all like one big microprocessor, and that's really what you're looking at. And this is only one wall. This thing actually spanned like the entire room. It went across the back wall, and there's other pictures. That it was like literally a CPU that took up, yeah, the cables are for, whatever cables are for, yeah. That's how it was programmed. I left out a lot of the layout diagrams, but I also included things in the slides that have some scans of old diagrams that were programs, or like how the machine was wired up. They're actually hard to translate, or hard to visualize in terms of how that wires up to this, but much like a schematic, an electronic or digital schematic now, you know, versus a real circuit board. I mean, obviously one is just a representation of the other. Some of those are the same way. So they didn't necessarily show like what thing plugged into what. It basically just showed the connections more abstractly, and then the programmers would make all the connections. Dials being data, effectively, you know, hard-coded values, the cords themselves being how that data would flow through the system. There were, you know, addition, multiplication, you know, simple division, the ability to have lookup tables for, you know, that's what some of these values on these switches were for. Actually, over here, if you can see, kind of in the background, and there's tons and tons of pictures of this machine now. But these quote function tables could be set up. So for like sine and cosine, the system didn't have that kind of power to compute those, but the values could be kind of preset. So if you're, say, calculating a trajectory of something, then, well, basically how all these switches were set representing a, say, sine cosine lookup table that kind of fed into these were wired into the whole system as well. It says, oh, I need the, cosine of, I don't know, 45 degrees or something, just making up numbers. And, well, you'd get a rough approximation and it would move on. Of course, everything was done with, integer arithmetic or fixed point. Not even really numbers per se. Of course, that applies to regular computers as well. They're just bits. They're not really numbers. They're just on off. And it's up to somebody else to translate that into, something workable. But yeah, it's a fascinating piece of hardware. This is kind of an aside that I threw in because of the fact that it's really from like one of the earliest eras of sort of most people's exposure to computers. And it was a system called Plato, which started in the 1960s at the University of Illinois, I believe. Check my facts because I linked things there. But I'm just going from my own memory that I think it was University of Illinois, Champaign, Illinois, I believe. And it was a huge mainframe system, and there are other pictures that exist of the sort of operations. But there were these terminals that, this terminal right here is probably from the late 1970s, just by the looks of it. I don't know its exact date, but actually, if I zoomed in, I could get the exact date. But I'm guessing 78, 79, maybe 80, somewhere in that neighborhood. But yeah, it just connected to it was a terminal to a mainframe system. It's kind of just another illustration that it was like literally 25 years before Blackboard. Honestly, it was just an opportunity for me to get a dig in on Blackboard, I guess. They like to, claim they invented lots of things that existed 25 years ago. But literally the system had like a classroom management system type of thing. It had email, it had, student instructor feedback. It had the ability to create online lessons. It was a pretty incredible feat in an era before people actually even owned computers. There was terminals that were set up. You'd have entire labs set up with these things. And it lasted quite a while, surprisingly long time, through successive modifications and stuff. The Plato system went into like the mid-80s. I remember even seeing some of a little more modern version of these same terminals when I was a kid in the 80s at school. It was part of the Plato system, but it was really kind of being retired at that point. It was retro even then, but still being used. The first machine that anyone could actually ever buy, like the average person. I mean, if you bought one of those little Plato terminals, what were you going to connect it to? You didn't have the mainframe or the dedicated lines to connect to the mainframe somewhere else. So basically, the first machine that a person could ever purchase was literally this thing called the Altair. The Altair was kind of interesting.
You are watching Towson.
Turn off the volume there because I just want to scan through it a little bit. The Altair, I can find where I want to, go here, just right there. Was literally programmed like you didn't need a monitor. You didn't need a keyboard necessarily. You didn't need any input-output devices because it had lights. I was talking about the era of the 1960s. It had lights built into it. That here's where I was trying to go with that. That would allow you to program it. However, I don't know if you recognize either of these two people. Let me zip back. There we go. Bill Gates and Paul Allen from a bunch of magnetic tapes behind them. from the 1970s, and early pictures of Bill Gates, Paul Allen there, that a version of BASIC, the basic programming language, was developed for this system, and literally the first PC software that was commercially available to the average person. Like if you owned an Altair, you could buy a copy of Microsoft BASIC. And I won't bore everyone with just watching the bunch of videos now, but
maybe they had some software people. They were just going to go charge off and do this thing. Because we'd never had the chip, just the book from Intel, if we'd made any mistake in terms of how the instructions worked, the thing never would have run. And so Paul was scheduled to fly out to Albuquerque. He decided to go get some sleep. I stayed up all night reading the book to see if we'd miscoded some of the instructions, and finally decided it was all okay. Punch out the paper tape and made sure Paul got that before he went off on his plane. He wrote the bootstrap loader. That is the thing you have to key in to make this computer smart enough to know to go get data off the teletype to read it into memory. He wrote that on the plane on the way out, loaded it up in the paper tape. The first time, for some reason, it didn't work. The second time they loaded in, and it worked. So it came up, said ready, and he typed in a program. Print 2 plus 2, it worked. He had it print out squares and sums and things like that. And he and Ed Roberts, the head of this company, sat there, and they were amazed by that this thing worked. I mean, Paul was amazed that our part had worked, and Ed was amazed that his hardware worked.
And this was the first piece of Microsoft software.
But anyway, I just wanted to share that little piece of the clip, and in the slides here, which will become available at some point. I went through, and I just left the whole videos where I found them interesting instead of just cropping them. But yeah, it's a little piece of computing history there. The other place you might have seen this machine, or at least its clone, recognize the scene over here.
Can't say I recognize it, no.
You can't. It's from the movie War Games, back in early 1980s movie War Games. It's a classic Matthew Broderick movie, directed by I'm now just drawing a blank on the guy's name. The same guy that did like Ferris Bueller's Day Off and 16 Candles and all those movies. Hughes. I'm just drawing a blank. Drawing a blank on the guy's name. Basically wrote like almost every popular teenage movie of the 1980s. But War Games, if you haven't seen it, it's probably one of the best. And it is kind of an interesting take on the kind of the future, or what was, kind of considered the future at that time. And I used to have one of the, there's not a good view of this monitor here, but I actually used to have that exact same monitor. But these two things right here are just the same system. There was another company that basically just licensed the stuff from Altair, had a different design. The switches were lever switches instead of toggle switches, whatever. But in order to get anything in and out of it, teletypes were used. And if you've never seen a teletype, I was gonna blow this up. Whoops, this way. Front, sorry. Let's fix that. The teletypes were really the things that predated typical keyboards and monitors. Monitors were kind of expensive. Obviously, televisions existed, but paper. You'd punch in your keys, and well, you type, and it would just print it out on the paper, which would also send the data to the machine. Any output would just come back to the paper. as opposed to being, a screen and keyboard. It was, your screen was basically just kind of a rolling sheet of paper. But speaking of basic, what I think is really, really kind of funny is that with the very first piece of, quote, software, also came the very first software piracy. And if you look at the bottom, who wrote it, but if you can, I'll give you a moment to read that, if you can. It's legible. And in the slides, I also have I just attached a copy of the PDF, the scan. But even if you didn't get all the way through it there just yet, I want to blow up just a little piece of it here. There we go. But what about all the guys, resell, whatever. It's basically, a Bill Gates rant. I mean, but he's probably correct, in his overall assessment. His tone is kind of, frustrated, of course. But, the point is that, hey, you sell the first piece of software, you get the first case of software piracy. And I just think it's an interesting piece of computing history, simply because of that fact alone. And keep in mind that this is literally 1976 when this happened. So that's the I think kind of interesting bit there. Again, it's nothing really to do with retro computing, so to speak, specifically, about the technology, but maybe a little bit about the origins of Microsoft that you might not have thought about or might not have known. Literally paper tape and and the Altair. So let's see how much time. Okay, try to keep this relatively short. One of the to kind of get into the real modern things. We've got a little late start here. But getting into the modern, kind of computing, and by modern I mean sort of the era of actual displays, modern retro computing, whatever. Nearly every machine starting around the 1980s, sorry, late 1970s, was tied to how televisions worked. The television itself, the old CRT style television, was key to the internal functioning of almost every machine made during that era. At least that was for home use. And I'll show you some of that idea in just a second, but literally the idea of how a television works, understanding how these televisions work, and I'm sure that there might be some old CRT televisions still floating around somewhere. I actually have one in our basement where I have my kind of retro computing stuff, my collection of old vintage systems and whatnot. It's always good to have a real life, cathode ray tube, television to be able to, well, not have to use emulators and so forth. I want to just play a little clip of...
Hello there, my name's Gavin, and welcome to this episode of the Slow Mo Guys. Very odd.
The Slow Mo Guys, they have a YouTube channel. I don't know if you've ever seen them, but I just want to go to where they really slow it down here. That one of the things about, and this is important because this is how do televisions actually produce a display? Look at that. I don't know if this is coming across in the Zoom session very well, but they're really slowing it down. The way televisions work is they scanned from top to bottom, but so quickly that, to the human eye, it looked like it was a single, a single frame. So as you can see those scan lines going across there, that is quite literally how the computers themselves of that era rendered video, and how, as a programmer, how you even had to think about it to some extent, like the Atari 2600, the original, or one of the most iconic game systems out there. Literally, you had to program on a scan line by scan line basis. And that just seems totally bizarre, but it's like seeing it in slow motion, or how they work in slow motion. Of course, there's first-person shooters and whatnot, but seeing how they work in slow motion
retains brightness. It's the
is, I think, kind of critical, because of the fact that when systems finally came out, do that a little bit later, like, well, even though that was a picture of a Nintendo, their Mario Brothers, the original game Pong, for example, well, it was basically an implementation of how televisions worked. Now, I didn't include a video of the game Pong. I'm assuming everyone has seen the game Pong, or is at least familiar with it. I guess I should have included an image here. Maybe in the final version of the slides, I'll add that. But I'm sure you're familiar with the entire game of Pong, where it was simply a matter of, I'll show you an image here. It's the original arcade machine, but there we go. This is kind of, let me blow that up there. Probably hard to see a little bit, but this is like the original Pong arcade game, and that's like one of the very first video games to appear in arcades, just bouncing a ball back and forth. Of course, the object was to win and not to just bounce it back and forth. You didn't get points for that. But again, just Pong. I should have included perhaps a snippet of that. But that's how these machines, that's really what these game systems did. Now, when I was really little, I remember we had a Super Pong thing. We had this one over on the left here. Telegames, actually, or was it a Telegames? No, I think it was my cousin. Now that I think about this, that I was jealous. And now that I actually speak of it, I remember, because we had Telegames was a kind of a licensed subsidiary of Atari. If you look real close, there's an Atari logo, still there on the little button. But that was just the basic Pong. But then Super Pong had other modes, like playing against another, or playing against the computer kind of thing. But the reason I bring any of this up is because what kind of processor did Pong have? How much RAM did Pong have? Anybody know how much? It's a trick question, really, because the answer is none. It was literally designed purely with digital circuits, discrete electronics. Now, this is just a schematic. I'm not going to pour through the schematics. If you have an electronics background, you can probably recognize, what some of it means. But literally, it was driven totally by just discrete electronics. Like everything you just saw there was like Pong just working. There was no CPU. There was no RAM. It was all just electronics drawing things on the screen, that television, at the proper time to be able to position the little paddles, to position the ball, and respond to the, potentiometers, so turning of the dials. to make things work. And it's really kind of fascinating that they were able to pull this off with literally no CPU whatsoever. But you know, a little bit later on, of course, CPU started to emerge, and the quote 6502 processor was one of the most iconic CPUs of all time. This CPU, this processor, was the backbone, the workhorse of the Apple II. It was just of pretty much everything. Like almost, you know, if you've ever heard of a machine that existed in the 1980s, it probably had a 6502 in it. That's not exclusively true, of course. There were other CPUs available, the early Intel, you know, 8080, 8088, you know, so forth. But most of the really iconic machines all ended up, you know, with this processor. The reason for which, and we could dig in to lots of detail just on the history of it, but the main reason was it was cheap. The guy who designed it, or who's lead at this design team, is more than one person. The person who was the lead designer, a guy by the name of, well, Chuck Peddle and Bill Mensch, I know, were the two kind of main people. One did the sort of circuit design, and the other did the layout, so they kind of worked together, I should say. They worked for Motorola at the time, and they were selling a CPU that cost like around $350, you know, to make, and well, that was their selling point. And these two guys said, you know what, we can make a much cheaper version. Motorola didn't want anything to do with cheaper. They wanted to be able to sell the, you know, things at a nice markup, at least as the story goes. So these two guys, Bill Mensch, Chuck Peddle, went off and were able to create a processor that was literally like $25 cost, and probably less than that, you know, when purchased in bulk. And so this is still like early or late 1970s, and that's why a lot of these machines ended up using it. But it's also iconic because it was brilliantly designed. Part of the ability of it for it to be inexpensive was because of its just sheer brilliance in how it worked. And I'm just going to skip some stuff that you can go back and look at the slides in you know, on your own. But you know, to this day, this processor has like a fan club. People have built, it's called the Monster 6502 project. Some guys have been working on it for years. That, I mean, it exists in kind of different forms. That you can see kind of the size of it there. You know, the size of a full-blown, or even bigger than like most circuit boards or most motherboards in PCs, that like reconstructed the entire processor using just transistors and discrete logic components to basically replicate the entire processor. So, you know, it's kind of fun. You can see an Apple II sitting here, Apple IIc by the looks of that, or maybe it's an E. Atari 800 XL, Atari 800, you know, just some things there. But what's really kind of fun, kind of getting into this kind of retro computing idea, is that around the year 2010, another group, and you can follow the links if you choose, got together and decided to, quote, reverse engineer the original version. The original version of this machine, or of this processor, existed purely in like, well, what they call lithograph, you know, where they had these huge sheets of like, were basically plastic. That's how they would carve into like these different layers of, like, when they build up the CPU. Instead of, you know, CAD software like we have now, they would literally cut into these pieces of plastic that were pretty massive, and then use ultraviolet light to kind of shine through these big things through lenses and focus it down to something that was on a chip to be able to etch onto the chip surface the various logical components. So I'm trying to, this video won't, or this image won't open, but here I will just kind of show, I'll show one of these here. It'll take forever to load, but, and this is actually going somewhere kind of interesting, because if I zoom in here, you can see that the CPU, it's a huge image, and it's just kind of causing, yeah, you can see how slow it's loading because it's just massive. It's just the site. There we go. Just zoom way in here. This is through like X-ray, using magnifying microscopes and everything else that kind of etched off the surface of the processor, kind of how they were built in the early days. Most of the modern replicas of the 6502 are just based on the operating, or just kind of its design criteria. So it's a re-implementation. This is a project to go back, again, in preservation, like the ultimate in kind of retro computing, going back and looking at, well, how is this processor built? When, interestingly, it was done completely by hand. It wasn't a computer-assisted design. It was completely by hand, through these multiple layers. So some bright people decided, you know what? Let's simulate this thing. And this is where, if anyone is interested, we can do a little, tiny little walkthrough of something. There's, I'll hone in on this website, and if you have the ability to launch a like a browser or whatever, separate browser with this URL, and I know it's kind of tough there, or just type Visual 6502 Remix, Visual 6502 Remix into Google, you'll most certainly come across the proper site, Visual 6502 Remix. I am going to expand that and go to that site, because this is where it gets a little more interesting. This Visual 6502 Remix, and I'm going to actually blow this up full screen where I can kind of see the whole thing, and I'll do a reshare in just a moment. Okay, resume share. This Visual 6502, we can actually run this processor and literally observe what happens when code runs. If you did go to the Visual 6502 Remix site, the Remix version, just the guy who did this has basically created like a little IDE out of it, a little development environment that allows you to actually run code and watch what's happening on the processor through an actual simulation. And there's videos and stuff about the whole history about how this was done. But they basically used those images, these various layers, and were able to reconstruct the kind of working operations. So what you end up looking at is a complete functioning version at the transistor level, the circuit level, the gate level of a CPU from the 1970s. One thing that you can do here, and this is kind of fun just to kind of see how this works, works a little bit. Oops, I want to go back to my slide here. So that's where my code is. I might just move this for a second so I can. Oh, Pong, somebody asked, Pong originally written for an oscilloscope. That was actually Space War. Space War was written for an oscilloscope. I noticed that. Pong might have been prototyped on an oscilloscope, but ultimately it was targeted. Well, they wanted it to be sellable in people's homes. Of course, most people didn't have homes. Most people didn't have oscilloscopes in their homes. So, you know, obviously the television, it may have been prototyped on a scope, but yeah, the one that was originally done on an oscilloscope was a thing called Space War, which was an early arcade game. Actually, Atari released that in their 1972 or 73. It was like one of the first video game systems ever, like arcade, you know, systems in bars and things like that. But this is something like interesting. If you want to actually do just a little, you know, example of, you know, programming the hardware, which is effectively how you had to program a lot of these machines to, you know, to begin with. This tool actually allows you to do that. Under the View option here, they actually have an assembler. And instead of having to enter codes manually, you know, these numbers here, instead of having to enter all those numbers manually, we can actually use a real assembler. Now, what I'm going to do here is this MOS 602. This is like its memory. I'm just going to select one. I'm just going to hit 0. I'm going to just hold down the 0 key to kind of wipe it out. It doesn't wipe its own memory out very well. Again, it's just a little simulation. And I apologize for the font here because there's no way to really blow that up, at least in this environment that I'm aware of. I've toyed around with it for a while. But we can start writing tiny little programs like LDA, load accumulator. Basically, there's only a couple registers in this machine. It only has an accumulator, which is basically just a register where every major operation occurs. All the arithmetic, you know, any type of mathematical operations generally through the accumulator, and an X and Y register. So 3 8-bit registers. So if you've studied like through 290, talk about, you know, CPUs a little bit. Well, this one only has 3 8-bit registers, period. Aside from a stack pointer and a program counter, which might have talked about at some point, that just to keep track of basically what the machine's doing, status register stuff, but really only three major registers. So I can write a little assembly code here that says, you know what, I'm going to load something into memory here. I'm going to load, and this pound sign stands for immediate mode. The dollar sign there is, let me blow that up a little bit for you. This here, oops, zoom share. I help a little bit. Dollar sign for hexadecimal. So I'm going to say load the accumulator with FF. That's it. Oops, it also has to have spaces in front of it. This is a common thing with assemblers of the era. You have to, the first line is, the first column is reserved for labels. So yeah. So LDA, load accumulator, you know, FF. FF is just a hexadecimal number, 255. This little up arrow is a reset button, and I'll actually just step. And we can watch what happens as I do that. As I take a couple steps, the accumulator has FF in it now. I apologize if this is kind of small to see, but I just put a value in one of those registers. I can hit this up arrow for reset again, and I can maybe load a couple of things. I can like load the X register with, again, the pound sign is necessary because loads by default will try to read something out of memory. Here I want basically this just saying store a value. So A9 is the code for load accumulator, at least in this mode. FF was the thing I'm putting there. Let's try a couple other ones here. Like, I just use 128 without the $sign in front of it. Just say, well, that's a decimal number. You know, LEY, that's a Y register. Again, the £sign is there for immediate mode, meaning sort of just do whatever. I just load that value literally for literal mode. Probably a better way of saying it. Reset that. We can see we got some code here. We can see we got the FF in there, the 80, 40. Well, 80 is just hexadecimal for 128. 40 is hexadecimal for 64. And you know, if I take a couple steps, there's two buttons here. Well, half cycle. It's just the way the processor works. There's, you know, the every cycle, you know, has basically two parts. You know, so top part and bottom part. But it did operations on each of those. So half cycles or full cycles, doesn't matter. But we can see that FF went there. Let's see, keep going. 80 went into the X register. 40 went into the Y register. And like literally, this is as close to the real processor as you can get without actually having a real processor. I'm just going to do a quick little example here again, just to kind of save us some time. What about a little loop? Here's a little test. It's on the slide that I put together. Just to show, I'm going to zoom way in on that. There we go. Just that's the code. Load the X register with a 0. I want to create a loop. But I want to just store the X register in memory location 20. Again, I just kind of picked that one because it's easy to see on the screen. Load it into memory location 20. TXA. That's the assembly mnemonic for transfer the X register to the accumulator. So we move a piece of data from one place to another. Store that result, store the accumulator in memory location 30. Again, this isn't meant to be a complete lesson on assembly programming, just a kind of a little idea about kind of how these things worked. Store that location 30, but the comma X there, that was the mnemonic for that location plus the value of X. So if I want to store something in memory location 30, well, okay, great. If X is 0, that's what these index registers are for, X and Y. It just adds them. So if X is 0, we store in 30. If X is 1, we store in location 31. If X is 2, we store in location 32. INX, increment X. The X register, or the X, the X register. BNE, branch if not equal. Well, not equal to what? The only thing you could compare to, well, not the only thing, but without additional instructions, 0. So things looped around. Once it got to FF or 255, it would wrap back around to 0. So keep branching while it's not a 0. And I'm just going to run this little program here. I'm just going to put this in maybe enough that you can kind of see some of the gates going, and just go ahead and run it. And I'm going to 0 out all these. It doesn't. One thing about this little simulation is it doesn't have a nice reset. But play. Oh, it does this sometimes. You have to stop it. Kind of reset. I'm on step. Am I in the right? Okay, there we go. Step back. All right, it's being this site off. I found that it often has some weird issues that if you catch it in the wrong cycle, there we go. I wiped out my code there. That was the problem. Okay, there we go. catch it in the wrong cycle, it sometimes doesn't quite work right. As you can see here, you can see numbers accumulating. Let's see, blow this up a little bit more. 15, 16, 17, 18, 19, 20, or whatever. It's filling in the memory. 1, 2, 3, 4, 5, 6, 7. I know, it's not all that exciting, but it is literally the CPU. Now, why did I bother going through all this stuff with the CPU? Like, okay, well, because it's cool. This is an example. This is the kind of retro computing thing that a lot of people are spend time on. That recreating old hardware that no longer exists, and the ability to, well, basically interact with that old hardware in some virtual way. Emulators, for example, which I'll draw this to a close here pretty quickly. I won't go through every single slide, but again, once we have this processor here, once we have some sort of emulated processor, we can actually start to build emulated machines themselves. And give me just one moment so I can come back to this and kind of reshare. And again, these links are all in the slides and the the code I used. Excuse me. The code I used is all in the in the slides. But where the television and CPU kind of come into kind of start to converge a little bit is the idea with these with emulators themselves. Whoops, resume share. Emulators themselves. That, for example, I can run the old Atari 2600 game Adventure, which I'll do in just a moment. It won't be Pitfall, it's Pitfall shown there. But here, this is like, to a programmer, like this thing called the vertical blank. Well, from the television standpoint, that was like the area above the display. Here's the area below the display. What a person saw watching television, like when you were watching TV, you didn't see any of this. But it was really happening behind the scenes, just the way the television worked. Like what I just highlighted there, that's what what you saw. But, so blow that line up a little bit and do this. Oops, not that. Do this. There we go. So this might be, what you actually saw. I do have Pitfall and emulator here. There we go. I'll pull this up in just a moment. But this vertical blank, that was time really that your code had time to be doing something. Remember I said that you had the program with that processor, directly to the screen. So during the screen draws, your code actually had to be, for the Atari 2600, the code actually had to be writing to that screen. And there was a little bit of space above or before, and this is all stuff that it's all part of the television standard. And while the TV was doing its reset, effectively going from one scan line to the next, there was this thing called the horizontal blank, where like 90% of your computations had to occur. And there was also a little delay between frames where you could do additional computations or run additional code. But clear this and show this. Here is, maybe we can fit it kind of right there. We'll pretend. This is an emulator called Stella that, you can see what it looked like, the Pitfall game. Oh, and I probably can't see it. Where'd it go? Oh, it's on my, uh-oh, I'm getting hit with stuff. I actually have the Pitfall patch. When I was a kid, the company Activision, like if you got a certain high score, you could literally take a picture of your screen, you know, with an old Polaroid, you know, camera, and send it in, and they would send you like some prize for like getting so many points, which was usually like patches or buttons. And so yes, I have a bunch of those from when I was a kid. Sounds terrible, but here, the reason I decided to load this is because any of these types of tools have debuggers built into them, where we can literally watch what happens as the game runs. Now, I won't get into the entire Atari 2600 architecture. That would take way too long. But suffice it to say that it did not have bitmap graphics. This machine had 128 bytes of RAM, literally 128 bytes of RAM. Cartridges that would plug in had an address space around 4K, 4 kilobytes. So it could read like ROM that was about 4K, but in terms of like storage space, literally 128 bytes, that's all the more you had. So there was no image, there was no like bitmapped graphics, you know, load in an image, store it in memory, and then display it. None of that existed, at least at this time. It had to be programmed by loading data into various registers, and this down here was the quote playfield register that had to be basically loaded data into these memory locations that would display at the proper time. And there are all kinds of toolkits out there, you know, for this, but let me trace through. I'm gonna hit the scan here just so you can see what happens there. Okay, there we go. That as the code runs, notice this stuff going on right here. Like, this is what's fun about some of these emulators, that you can see it's just kind of showing in gray, kind of grayed out what the previous frame was, and then drawing down scan line by scan line, scan line by scan line. Let me just do an individual trace here so that we can actually see over here. You can watch what happens as the program kind of sort of runs. This little dot that's moving across here, literally that you had 3 pixels. The trace on the screen would move 3 pixels for every CPU cycle. So even if you were trying to run code, you didn't have that much time. The code itself had to have everything set up, and changes could only be made like maybe a dozen. I mean, it happened so fast in the screen drawing that you had maybe the opportunity for a few dozen machines or instructions. And of course, it would kind of go through and draw its thing. The playfield is staying the same there just because of the way they did the playfield. Is all the trees. Let me go through the scan lines. The reason these are all green like that is because they're the trees in the background. Here, let me just skip ahead there. There we go. We can see weird playfield things there. I'm just like, well, wait a minute. There's only two things lit up. Like, literally, the playfield is nothing but, well, 8, 16, 20 bytes. Like, literally 20 bytes is what you had. But there were all kinds of like these weird other registers were like duplicating things. So stuff like this would happen. Let me just grab this. Like, if you wanted this tree here, there was a replicate that would replicate on the other side. That was one of the options. So like this right here, it was really probably these 2 trees. Let's see, this right here is most likely these 2 trees. I haven't traced it out, but most likely because they would actually replicate. This is only 1/2 of the screen, like that data. You only had enough information even for half the screen, and it would flip things on the other side. And there was control for whether you displayed it or didn't display it, or whether it was reversed or how it was mirrored and things like that. But that's why so many games from this era all have symmetry to them, is because you basically had like only enough time to control half the screen at any one point and had to replicate that or flip it around least for your backgrounds, for the other parts. And let me just advance through this, and I want to wrap this up here in just a couple of minutes. There's a bunch more slides I had, but we started late, and I don't want to hold everyone up. But you can see that as we get into, let me go frame our scanline mode here. This will change these up a little bit. There we go. We can start seeing what the crocodiles might have looked like and so forth, but here we go. This is part of, if I can trace this here. Where's my trace here? Trace. I'm already past it. But even the little scorpion down here, let's see, trace, keep tracing, there we go. Notice like these bits right here correspond to really a portion of the thing being drawn, basically just on a single scan line. So it must be the one right above there. And like I say, don't want to just make everyone watch that. But in either case, there we go. Here is part of like the word Activision being drawn. Let me clear that. This right here, here are the letters for the word Activision. And watch how they change. It's like, oh, there's a few there. Let's see, and I have to be able to predict, see, okay, well, there were two sprites in effect. So they're combining two different sprites to make up the word Activision as they go across and display that. So it was not an easy machine to program for. That's for sure. There's a great talk on this entire architecture if you really want to get into it. But just in the interest of time, one of the last things I'll show and then just kind of mention a few other things is that there's this 8-bit workshop. It's another site that that's listed there. Whoops, 8-bit workshop. Where you can actually start playing around with all this stuff. This 8-bit workshop is a really, really cool website. And I honestly discovered it while I was kind of putting some of this stuff together. Atari 2600, they have different kind of game consoles, NES, Atari 2600. Oops, let me just go to Playfield Graphics. There we go. I've made a couple small little modifications to this just to kind of show how it worked. But basically little tutorials on what the code looked like. These like vertical blank things. It's like, oh, well, that means wait for the scan line on the TV to come back around to the next line. Or actually, yeah, the vertical blank is actually for the next frame, sorry. W sync, that's wait sync. That's for the horizontal blanking. That's the wait for the next scan line. Sorry, I had this backwards. You know, the color of the little things that might be drawn on the screen. Let's see, other playfield things that can be drawn. We can kind of play around here. Let's see, I'll let the colors kind of, oh, there we go, we got some background color. You can play around with some of the values in there if you really, really want to, but well, yeah, that's pretty much the complete program, just to start drawing some things on the screen. There's some nice tutorials in here, which I think are pretty cool. I'm just kind of drawing this to a close here on how to program for this type of system. How to like draw basic little things on the screen and how to get just various little bits of graphics going. Let's see. Let's see. 2. There we go. Let's see. 3. Let's see. Got different kinds of things there. Let's see. Width. The width of things. Anyway, we could go on forever. Yeah, I could spend days just on tutorials about how to move things around on the screen. But it is kind of nice because it does have some samples, a little Space Invaders type game. It's very minimalistic, not quite complete, but you know, things aren't moving. But again, you know, kind of how to build all that up. And finally, just to let us go here, I want to say like why some of these machines became so popular in the 80s. Like here's the Atari, you know, 8-bit line. All of these machines were kind of the same. They're basically just different variations. And I'm just kind of plowing through quickly here, kind of at the end. Here's what the motherboard kind of looked like. I just grabbed an image here from somewhere. Here's what the motherboard looked like from a machine that, well, hasn't been altered. Beside me, I actually do have a real Atari 800 XL machine that I was going to pipe through. If anyone wants to stick around and see stuff later, I don't know if it's not showing up. Oops! Oh, it's not showing up as me. Oh, there we go. I have a virtual background, so it's trying to think this is the virtual background. That's funny, but yes, it is a real Atari 800 XL. Here's what it looks like inside of mine at this point. Yeah. This is how upgrades were done. Added extra RAM, different switchable firmware for the operating system, second audio. Well, that chip did a lot more than just audio, but the second chip for that to get stereo because they were just mono at the time. Tons, like 4 different toggle switches on the back that had been added over years. And I didn't do all of these in high school. Some of them were done in college, some were done in the 90s, some were done actually a couple years ago when I kind of got into this like nostalgic theme again from doing some retro stuff. I'm like, let me do some more soldering on this old machine. They were the Raspberry Pis and the Arduinos of their day to some extent. But one of the reasons that they were so incredibly popular is because, this is where I'll finish up, just so we can all go our respective ways. The reason these machines were completely different to, and this is the only time I'll say, you know, like in my day and, you know, in my generation, you know, just about how different things were. That, you know, this is an Atari 800 running as an emulator, that when the machine booted up, when the machine first booted, you were, the first thing you saw was a ready prompt. Well, ready for what? Well, ready for basic programming. That the basic programming language was built right into these machines. Print, oops, you know, print hello. Yay, print hello. Oops, I have a program that's already in here. So I'm not going to run a complete program right now because I'll trash the one I have. But the ability to do graphics, I don't have to really type the whole thing out, but let's see, go to graphics mode 3, split screen. Let's see, color 1, let's see, plot 10, 10. I'm in a very low resolution mode, just to make it easy to see. But, you know, circle 10, 10. Oh, circle, I need, that's location, I also need a size. I need, there we go, 7. Ah, there we go. Very low resolution mode, but you could like immediately start playing around with stuff. The computer booted you into a programming environment to a great extent. So that's why, like a lot of the quote, kids from the 80s, about basic programming and stuff, but how many computers just boot you into a programming environment now? Like none, really. But that's kind of what you had. And you could load programs, and you didn't need to go into basic. Obviously, you could do all kinds of other things as well. But when the machine first started up, that's where you were. Yes, I could go into. Oops, that's not what I meant for it to do. I could go into DOS, which this is a kind of a weird operating system. It's not really the one that came out a little bit later, but let's go back to. I'm using a thing called Turbo Basic, and it just crashed on me. The emulator crashed. I know this is a. Let me just speed that up there. I do want to use Turbo Basic for this, and there we go. And let's see if I can load my. Hopefully, my program didn't go out of memory completely. I have it on a RAM disk. There we go. A basic program. This is one that it was like a prototype. I found this when I was going through stuff, kind of preparing for this. Found this program that I wrote. I don't know when. I was in college at the time, but I spent probably like 2 or 3 days. I mean, not probably more than that, probably about a week on it. But where is my? Hold on, just one moment. I have an old Atari joystick, and I unplugged it. Oh no, unplugged my controller. Oh well, I'll just go ahead and run it. I have an adapter, a USB adapter that I can plug a joystick into. I don't need it. I set it up for keyboard as well, and I had completely forgotten about having written this. I was going through the code thinking, wow, like some of that stuff is, I'm impressed that I came up with that. And other parts are like, that's the stupidest thing. What was I thinking when I wrote that? But, that of course happens. And it's the emulator that's acting up here. So it actually did more than that. It's probably not worth going through here, but it is kind of interesting to see what you could do with relatively simple games at the time. And that's, yeah. And just one more here. Come on. Basic. Thing called Turbo Basic. Instead of the built-in Basic, but let's see. I know I have it on this drive too. There we go. Run. Oh, there we go. I don't know. I think that it just got corrupted because I had it in a RAM disk. But Air 50, I don't care about that. With built-in just character graphics. Here, this is, sort of the days of, like I say, just old 8-bit programming. Yeah, put that there. Sure. Well, I was actually proud of this code. Not proud of that move, but I was actually proud of my my programming there to some extent. And this was mainly meant to be a prototype. It was supposed to be in color and everything. I do remember, you know, now that once I dug it up, I remembered like, oh, I wanted to do so much other stuff with this, but that never really happened. Throw that there. I just want one more here. I mean, oh, it's not going to give me one that I want. You know, it's your typical columns type game. Clear those out. It will do it recursively. There we go. I didn't get anything else in there, but anyway, you know, the idea was, of course, that speed up the emulator here. Yay, I got the high score. That, you know, the machine they all had pretty much built into them, you know, a basic programming language that, you know, allowed people to just start tinkering, you know, right away. And of course, not all of this happened in one day or the day after getting the machine, but over years of, you know, having it. You know, kind of get to the point where, you know, it's just there. That it's not like you have to install anything. Though I was using a version of BASIC that was a little bit beyond the built-in one, a little more powerful than the built-in one, but that was really about it. And that's pretty much it. I went, well, honestly, kind of went to the time I would have. We started about 15 minutes late. So yeah, we ended up kind of where I wanted to ending up anyhow. But, you know, if anyone wants to get into like the whole retro computing scene, about emulators and things like that, just let me know. I'll be happy to chat with you and point you in the right direction. But as far as that goes, I have really nothing else aside from an illustration of the quote demo scene, which is basically just people pushing these machines to their limits. And I will just leave it at that. So, anyone want to talk about anything?
I don't got a question.
Oh wait, let me turn off the sound here. Yes.
So, earlier in the presentation, you were talking about BASIC and the first like at-home computer thing. Is that like so? You know Visual Basic, right?
Yeah.
Is that like a stemation of that, like the very first iteration of that, or
Visual Basic, or
is BASIC the first iteration of Visual Basic?
Let me just turn off this screen share here, because that's just going to be distracting. Not necessarily. The first version of BASIC was from Dartmouth University in the late 1960s, early 1970s, that worked with those teletype terminals. And it was a little bit even more primitive than most forms of BASIC. Like, for example, like the if statement had no else, because you don't really need it. It just had go to. It's like, well, you know, if x equals y, you know, go to line 20. If x equals, you know, well, you'd skip over things. So what became Visual Basic sort of kind of has some history going back that far, but it was so modified that I wouldn't even call it the same language, really. Yeah, it's kind of hard to say that with Microsoft Visual Basic, what kind of connections it really has to like the earliest days of BASIC. But what I was going to do here is share just this, and I'll just disable, because I'm just running an emulator here. Detach. There we go. Boot error. It's fine. let me enable the built-in basic, which I have, yeah, internal basic. Okay, well, I want to boot internal basic. Ah, that's probably because I have other things in there. Here, let me get rid of my other disk drives. Yeah, I want to just detach. Oops. Actually, I can just turn it off. There we go. The reason I wanted to do that is because there was a disk present, so it was trying to boot into, it was trying to boot off the disk. That's what basically this particular machine. If you had a disk in a disk drive, it would try to boot off the disk. Otherwise, it would just take you right into BASIC. But like the original versions of BASIC, didn't even have, like I say, an if statement. You have to do something like this. I might say, x equals 1, 20. If x is greater than 0, then go to line 30. Oops. Oh, but I forgot. Let's go to this. Print. Print hello. But I might have to do something like really ridiculous, like this. Let's see, line 25. Print goodbye, and start getting things out of order. So let me list my code here. Let's see, if x is greater than 0, print 30. Okay, and then line 25, goodbye. Let's see, line 27, I might have to go to line 40, and line 40, print done. There we go. Let me do another listing of my program here. This doesn't even understand CLS. Forgot how limited the built-in one was. But, a simple little program like this, run hello, done. It's like, what if I set, actually, let me get rid of line 10 altogether because I don't even need that. Here, list that again. It's kind of like interpreter. I can set x equal to 0 there. Let's see, run my program again. Goodbye. Let's see, x equals 1. Let's see, run my program again. Oops. Huh, that's interesting. Let's see. My program again. List. Oh, I forgot this version of BASIC. It's been a long time since I've used this version of BASIC. I forgot this one actually did set, did clear out the variables when you typed run. Some of them didn't there. But yeah, it's a far cry from what became Visual Basic and all those languages to follow.
Makes sense. I thought because the name, like Basic, Visual Basic, Microsoft.
Yeah, Basic just really stood for beginners, all-purpose, symbolic instruction code, and that it became synonymous with being like an easy language to learn. And I honestly believe that, given the dramatic differences that Microsoft did have their original version of BASIC, Microsoft Basic, from the Altair and stuff. And in fact, even for the Atari line of computers, and there was Microsoft Basic. However, like what they did with Visual Basic was just such a completely different language. I think they just used the name to make it sound nice and friendly and easy, even though it was so different as a language. I'm speculating, just guessing on that, but from seeing it, that's kind of what it looks like. But anything else on that? Looks like everyone took off, or most everyone took off. So I hope that wasn't too awfully boring. I know it's kind of rushed at the end because we started a little late and I was trying to just wrap it up, because there were only a couple of people here. But yeah, it's fun to kind of keep those old machines around and play. And it's also amazing the technology that actually existed too, like the things that you could ultimately do. Yeah, I still have the old stuff. I still have, yeah, I have the Atari computer. I have a 2600 set up downstairs that, you know, it's not like I play it all the time or anything, or hardly ever. I do have, where'd it go here? Just for experimental purposes. There we go. This is, if you can, here, let me, well, actually everyone's in my classes. I just turned on the black background for the sake of not being too overly distracting. But I don't know if you can see this or not. It's an Atari 2600 cartridge that has an SD card in it that, like, from one of those sites, like that 8-bit workshop. And I did this. I actually played around a couple days ago, and, you know, just threw together. Basically, I just modified some of the samples and just kind of toyed, and copied it to this cartridge with the SD card in it. Popped it into the real hardware I have downstairs, and it worked. And, you know, I was able to play a game that I at least modified on the original hardware from 1977, I think. No, that was the second generation unit that came. That was like 1981, I believe that one was made. But yes, 40 years later, they still work. So it is pretty fun. And people are like adding all kinds of things, like, you know, those with the Atari, Commodore, you know, all those machines. People have added like Arduino units and Raspberry Pis like right inside to add additional RAM. You know, to basically we'll just connect it to the data bus and the address bus on the machine, and basically we'll use RAM. We'll use the Wi-Fi. People have built. And this is something I didn't show in the slides, but people have literally built things like this. This is from just the other day, or just like literally from a couple days ago, that someone did. I saw this article. Let me switch to this. Yeah, maybe shrink this down a little bit. This is. You can see the date on there, 23rd October, you know, whatever, 2020, that this little box that's plugged into the, basically just the I/O port on the back, is a Raspberry Pi, I believe, internally, a Pi Nano, hooked up to Wi-Fi. So the person added Wi-Fi capabilities and is pulling data down from one of the weather monitoring, you know, just NOAA or whatever, that you can get data in a kind of a parsable format, and wrote a little weather monitoring app in what looks like it's probably written in BASIC, just pulling data down off the internet on a 40-year-old machine. And you know, why? Who knows? But you know, it's just those fun little hacks. You know, here's a Arduino with the leveraging the SD card reader that someone did. So yeah, it's one of those things where, like, you know, the old saying, you know, if you have to ask, you wouldn't understand. You know, it's just, there's something about this whole like retro computing thing. It's like, why would people do that? It's like, well, if that's your question, then you're just not gonna get it. I don't mean that in a negative way at all. I just mean that, you know, there's a certain fascination that you have, or you know, or you don't, with just sort of constantly modifying and tinkering and tweaking, you know, this old technology. It becomes kind of a interesting hobby for a lot of people. I just don't have the time to do it anymore as much.